Okay, so this is about more metric spaces, more abstraction. And this is one of the really pays off, what pays off to use abstraction, and then sometimes pays off are the ones that you actually see some insight into concepts that you dealt with previously, and now you have a better view of them. So, and that is the idea of approximation of functions by functions. So calculus 2 approximating functions with polynomials, specifically Taylor polynomials. That's the answer. How do we approximate functions with polynomials? The answer: find that function's Taylor polynomial. That's the approximation. So that is, now we have a better view of that because we understand that it is we think of functions now as points. Okay, so we have a set or a space of functions, and then functions are just elements there, and but it's not a loose collection or set, simply a set of functions anymore, but it has a structure, and that structure is a metric space. So in other words, just like we measure distances on the plane, on the line, in the Euclidean space, on the surface of the Earth, and in a number of different ways, we can measure distances between functions. So that is how it is done. In green there, what you do is you subtract the two functions, and then so this is it. You subtract the two functions, and then take the absolute value, and then take the maximum of that function. That is the distance. Okay, so once you have the distance understood, it is understood as a metric space. So then approximation, as I have at the bottom there, that it is indeed explains why we have why approximation means what it does. It is you can literally think about as if this is my f, and then there's a sequence of Taylor polynomials converging to it. Okay, so that would be an illustration of that topic in calculus 1. Okay, so all functions are approximated by polynomials. So there are really so many polynomials that are everywhere. You take a space of functions, and it turns out that you cannot separate functions from polynomials because there will be always, no matter how close, how small a disk you take around that function, there will be a polynomial in there. And then as a result, you make those little balls around the function smaller and smaller, and there will be always, and there will be, as a result, there will be more and more polynomials in that disk. Okay, and then that creates a sequence of polynomials, and the easiest one is the Taylor polynomial, as it is designed to, well, a specific purpose. It is designed for a specific purpose to approximate at a particular point. So the claim implicitly made is that, so this is the calculus 2 reference. But if we want to proceed with this a little bit beyond, then we got to prove that this is a metric space. So this is a metric. So it has to satisfy the three axioms. They are not really that complicated, but it is really, we're going to rely on this fact over here, that in fact, well, let me state it in the form of a lemma. It's going to be helpful later on. So f g are continuous on AB, then so is the absolute value of f minus g. Okay. So as I mentioned before, it is uncomplicated. That's what we know about continuous functions. The difference of continuous functions is continuous. Firstly, and then also the composition of two continuous functions is also continuous. The other continuous function is, what's the other continuous function? We took the difference, and it is a continuous function, and then we do a composition, what I'm talking about. So this is f, this is g. Take the difference. This is the 1. Okay, and then the last step is what? The other function is the absolute value. The other function is the absolute value, which you know to be continuous. And so, say y is continuous. And then, so the two algebraic properties of continuity come into play here. The difference, the algebraic properties, meaning all the four algebraic operations, produce from continuous on continuous functions produce continuous functions that from calculus 1, except for division 1 you might divide by 0, and in the property number 5, which is not technically algebraic, and that is the composition of two continuous functions is also continuous. Okay, so the absolute value is continuous, compose that difference over there, which is continuous, and we have another continuous function. Okay, so the whole function is continuous, and that is why as we discussed yesterday, that is why the maximum is defined, because by the extreme value theorem, continuous function reaches its maximum value. Okay, so that's why the number itself is defined to begin with. Okay, but then there are still three axioms to verify. So let's take a look. So the definition is right here, and the definition of the distance. Okay, so that's my definition. The space is the set is continuous function on this defined on AB, real value. So we're not doing anything more abstract than that. And so we need to prove the three axioms. So axiom 1 is the non-negativity positivity. So naturally it is larger than or equal to 0, so there is no problem with that. That's obvious. The slightly less obvious fact is the second half of the axiom is that dfg is equal to 0 if and only if f is equal to g. Can you prove this? Right, right. So okay, so this is also obvious, right? So obviously the difference f minus f is equal to g, then f minus g is equal to 0. So the distance is equal to 0. Okay, okay. So done. Okay. What about the other way? So if the distance is equal to 0, then the two functions are equal to each other. Yeah, okay, so less obvious, but how do we go about it? So suppose this is equal to 0, then now let's follow on with this. So d of g is equal to 0, which means that maximum of this thing is equal to 0. Then what? This thing is equal to 0. What does it imply? The maximum. What is a maximum? It is really not. It is a maximum of a set. After all, there is nothing tricky about it. It is what I have here to the right of the maximum. It is a set of numbers, and I just take the largest values of those. Okay. But those numbers on the right, what do we know about them? These numbers. These numbers are what? What kind of numbers? Non-negative, yes. So you take the maximum of a set made of entirely non-negative numbers. What does it mean? Well, they are greater than or equal to 0, but then you take their maximum, and it is 0. That's what we're saying here. There can be only one case. All of these numbers are zeros. So all of them are 0. So in other words, f of x minus g of x is equal to 0 for each x, and that is by definition means f is equal to g. Okay. Okay, so two ways. This one is easy. D of g is equal to dgf. Subtraction, right? The absolute value, I guess that is a property. X minus y is equal to y minus x. Easy to forget, but comes handy here. Number 3, the triangle inequality. That is slightly more challenging. So d of g plus dgh larger than or equal to dfh. So, well, maybe I'll leave it as a homework. I guess to prove it, unless somebody want to try it. So, what is the challenge here? What? No. This is for any f, g, h. Any two continuous functions f, g, h, this is supposed to be satisfied. The challenge is here. The challenge is you can we have to invoke the lemma and the extreme value theorem. So in other words, these are attained, all three maxima for the f minus g, f minus g, g minus h, and h minus f. These three functions, that we take the maximum of those for each of the three pairs, and these three maximums are attained, as we know, by that theorem, by extreme value theorem. So they are attained or reached. Okay, the challenges might be different points. So where? Okay, so if it was the same point, we wouldn't have any trouble, because you just compare them across the value. So that it would be just we would be speaking of three numbers. So suppose they are all attained at the same spot, hypothetically, say now number c. Okay, so d of g is equal to f minus c, what is it? F of c minus g of c. Okay, if that's the case, gh is equal to f of g of c minus h of c, and finally d hf is hc minus fc. Okay, so if it's the same value, then it becomes a matter of why the sum of these is larger than or equal to the third number. That is simply like the triangle inequality for real numbers, right? So this is analysis. But it's not the case. It doesn't have to be the case, because these pairs of functions are, once they're formed, it's like three functions that have nothing to do with each other pretty much, and then the maximum value could be attained anywhere, and then you can end up with three separate numbers. Okay, and so which means that you have six numbers, and you cannot apply the triangle inequality for the reals. Okay, so that's the homework to think about. But let's suppose, let's just take this a little bit one step beyond and see what the geometry or topology of this space looks like, and the only thing for us to worry about is what do the balls look like. So what do the balls of this space in CAB look like? So in other words, B, say, F, R. Okay, so a ball, if you illustrate it on the plane that this is my F, except now it's a function, and then this is a ball, all the functions within are units from F. Okay, so that is the illustration that is reserved for metric spaces. What about functions? So if I have my function f here on AB, and this is equal to y equal f of x. Okay, so what kind of functions will be within the within R from F? Can you point out one or two to begin with? One function. Well, what about what does a function R units away from F looks like? It will. The answer is it is a kind of a snake, but that it is not the answer yet because it can be misinterpreted. But what you're saying is that to consider it, you create a snake or tube around this function. Okay, like this, a tunnel like this. So you step R up and R down. Okay, so in all directions, in the two directions rather. Okay, so then the bottom function is f minus R, the top one is f plus R, and the one in the middle is f. Okay, so which means that the top and bottom, there are at least two functions that they actually don't lie. It's inside of that ball because the ball has to have distance less than R. But that would certainly be a fact to take into account. So distance between f and f plus R is equal to R. Plus or minus, in fact. Okay, so just a shift because the difference between these two functions is exactly R. You don't even have to go and do maximum minimum. Okay, so just plug it in, right? If I plug into my formula over here, if G happens to be f minus R or f plus R, the whole thing will be equal to R. Okay, so the distance is R. This is not the whole story. Let's take it one step further. So, for example, I go with df f plus or minus, say, s, and the distance is equal to s, and f is less than R. Then I have a bunch of examples of functions that are in my ball right here. Okay, so that is, say, f plus s. So s is less than R, which means that it definitely fits inside of this ball, right? The distance is s, and s is less than R, so that function is less than R units away from f. Okay? So all of these shifts of the function are good as long as you don't go too far. They will be inside of our ball, or whatever you prefer to call it, a disk maybe. But are there more? What about other functions that are as close to R, to F as these? Are there more? So you see, these are exactly the difference between F and this function F plus S is exactly S. It is exactly S, but so it is an extreme example. So there are certainly more functions that are as close, and it probably would help if we just try to do something. Well, is this function within the ball? Why not? just the endpoints? What if the endpoints? Why is this so important? The endpoints. What if I have something like this? So is the green function close enough to f? No, because look at this. This. Yeah, if I take the difference of these two functions at some value, this particular value, say c, it will be larger than r. Right, so that green interval there is larger than r in length, and therefore this function does not belong, say it is maybe h, it does not belong to BFR because of that. That gap is too large. But other than that, it is not really look that bad. What can we do with that green function in order to bring it close enough to f, so we can say it's within r? What can we do with that green function? Well, how about we shrink it? How about we shrink it by what? Just make it narrower, but otherwise it could still swing. How about this one? Right, so this one is okay, say h. This one does belong to BFR because, once again, you see how far does it deviate from f, and it does not deviate more than r units. So there you go. So in fact, every function that fits in the tunnel, will be within r from f. So once again, every green function, doesn't matter how hard it oscillates between those two limits, as long as it stays within that tunnel, tube, hose, whatever, it will be within our ball BFR. Okay, so that's what the ball looks like. It is the function. You cannot point them out easily. It's not easy to illustrate the idea with a disk or a ball because the set of functions is so large. And if it's such a simple, seemingly thing as a ball, is very hard to illustrate without just pointing out one example. That's what I'm doing here. I'm pointing out one element of that set, and that function in green. So anything that looks like this will be in it. If it sticks out, the only thing that will make a function not to be within that ball would be if it sticks out outside of the tunnel. Okay, so once again, this one over here sticks out, and that is why it is no good. This one. That is the reason why it is not within that ball. So once again, doesn't take a function, pull it up, pull it down, create a tunnel. Every function that fits within the tunnel is in the ball, and vice versa. Okay, so the only requirement that we have is continuity, an additional requirement to that. Okay. So any questions about this? No? Okay, so let's take this and once again bring it back to calculus 2 and think about approximations. So when we're talking about convergence, Fn going to F in a metric space, so CAB, that metric space with this distance. So what does it mean? Of convergence of functions on that interval, okay? And the answer is we just use the definition, so we don't have to make up anything. We just take the definition of convergence of a limit of a sequence in a metric space, and so we just go, as always, for any epsilon greater than 0. There is an n such that n larger than n capital. The distance Fn to F is less than epsilon. Well, that's actually one definition, and so that's where the open ball comes into play. This is our open ball. So it means that look at that picture once again. So there is a convergence. There is a convergence of sequence Fn to F when no matter how narrow a tube we build around F, that the elements of that sequence will remain within that. Sooner or later, they will end up within that band. Okay, so that's what the convergence means. Okay, so that's one interpretation. Another one is also we saw is the second one is the distance converges. So dfn f goes to 0 as n goes to infinity. So this is a numerical sequence of numbers, numerical sequence of numbers, and it converges to 0. So that's another way to see it. So the maximum of x within AB, fn minus f, is going towards 0. Okay, so there is a word for it, which may or may not come up in calculus 2. There is a word for it. It's called this is called uniform convergence. Do you see why? What is so uniform about it? Well, this is what we can look at. It is uniform because it's opposite, or not opposite, but in contrast to pointwise convergence. So this is, let me write it first, pointwise convergence. Okay, it is very simple. It is fn of x is going towards f of x for each x. Okay, so in other words, we check out every one point at a time and nothing else. So in case you do not remember, well, I'm teaching calculus 2 as right now, next, in fact. So I have some illustration here that I have used. There is somewhere of, these are examples of convergence. So here it is. So example of a convergence of a sequence, a little bit off center, so that you can see convergence, right? Sequence of functions that get smaller and smaller and smaller. In the end result, the limit is the 0 function at the bottom. Okay. So now, in what sense does it converge? And it converges actually in both senses. So, but the original one, the pointwise convergence, is illustrated there on the right. You can see that little tunnel, not the tunnel, but rather a bar that I drew over here. This one. So for each x in the intro, I don't consider the whole function at the same time. I take a piece of it. Okay, and then what I end up with just numbers, and these are numbers. And then if I concentrate on this narrow slice of my function, then those numbers converge to the number at the bottom, which happens to be 0. Okay, so and then I do the same thing for each of the slices. So one at a time, vertically, I look at how the functions, the numbers converge, and that is called pointwise convergence because one point is considered at a time, and all you have to do is just to check all numbers, and then you have your pointwise convergence. But at the same time, we have here uniform convergence as well. Can you see uniform convergence here? So this is uniform convergence on the right, which means that once again, for every epsilon, sooner or later, the distance of the elements of the sequence will be within epsilon from the limit. The limit here is 0. This is the limit, right at the bottom. Limit is 0, okay? The constant function. So you see tunnels. You can almost see the numbers as well. So you can see that say I choose. How about I choose epsilon here? Then sooner or later, all the graphs of the function will be below that level. So that tunnel, that is the tunnel. I mean, if you take that tunnel, the ball around the limit function, which is 0, this times is going to be straight. And so what we need to look for is to make sure that sooner or later, though, those graphs of function will fit within that straight band. Okay, and they do. Look at it. Eventually they will be less than that number, which happens to be whatever, 1/2 or something like that. So that's one standard, and then sooner or later they will meet that standard. If you choose epsilon to be smaller, maybe here, then once again look at it. Sooner or later, all the graphs of all functions will be within that band. Okay, so yeah.
Are we making a ball around epsilon or around the limit?
The limit, which is the 0 function at the very bottom, it is the function we are concerned with. And when we make a ball around it, it is a band. Well, it is band on both sides, right? So I just ignore what's below it.
And is the ball made from the constant function of distance of epsilon, or how does epsilon factor into it?
To speak of convergence, right? We need this is where this epsilon starts, right? And so for every epsilon, we have to point out that n at what point the tail of the sequence fits within that band, and it does, right? So for example, for the first value of epsilon that I have chosen, the green one right here is, and everything that follows it is within that band, the first one. If I pick a smaller value of epsilon, the second one, it is not gonna, does not work out anymore for the green one and for the purple one. But the next one, the blue one, does fit this one, right? And then on and on, no matter how small you make that band, you will eventually end up there. By the way, on the right is an example of what can happen generally in what this picture might come from, where you see convergence of functions in an environment that is simpler than Taylor series. I just take any function that you see it on the right. You take any function f and then divide it by 2, divide by 3, divide by 4, divide by 5. What's going to happen to this sequence? They're pushing these coefficients, those factors push the function or shrink it towards the origin, and then that's what happens. It happens exactly. You can almost see it on the sequence, how they become smaller and smaller and smaller in a uniform way, and then you have a uniform convergence in addition to pointwise convergence. Naturally, if you think about it, if the whole function fits within the band, then certainly there will be same will happen with a sequence of numbers within one single slice. So it is the uniform is that they are converging in a manner that is the standard epsilon applies to all points at the same time. So you can logically compare these two as we have in the past, like this. So pointwise convergence is distance f and x, fx is less than epsilon. On one hand, for any epsilon, I should write it out. Okay, so how does it go? For every epsilon, no, not for every epsilon. That's the difference here. For every x, for every epsilon, there is an n, such that n larger than n capital implies that this distance is less than epsilon. So for every x, that's the first one starts here. However, now we'll look at the uniform convergence. It will be epsilon comes first, and n comes second. Okay, and then x and n. So for every x, and larger than n implies that same exact thing. Look at it. It seems like exactly the same thing, but the replacing epsilon and x, moving epsilon to outside of n, like this. That's what happens. That's what makes convergence uniform, or not rather non-uniform, is that either you carry it out separately for each location, or you do it for every location simultaneously. Which is what we see on the right, and that explains the word uniform. So the example here gives the example of uniform convergence, and a uniform convergence implies pointwise convergence. However, here's an example of when to show that indeed it doesn't have to imply the other way. So it works this way, but not that way. Okay, so uniform convergence implies pointwise convergence, but not vice versa. Here's an example. It's called teeth or function. So if we take our interval 0, 1, okay, and then we build a teeth of height 1 like this. Okay, and then we allow this tooth to slide towards the y-axis, like this. Let's build a couple of more iterations. So the second one will be the same picture, only narrower. The same picture, the same height of the tooth, but just narrower, and then even more narrow, like this. Okay, so let's examine what we've got here. So the height is once again 1, remains 1. So let's look at the pointwise convergence first. So I pick a number, x. Say I might pick it here, x, and then sooner or later, the tooth will pass x. Sooner or later, after enough iterations, sooner or later, x will be here, right? So x will be lying to the right of the tooth, and therefore the values of all the functions following that moment will be zeros at x. So f of n of x is equal to 0 for large enough n. Okay, so what does it mean? It means that we have convergence, right? So there is no literal convergence. They're all equal to 0. So naturally, this thing goes to 0, right? So the limit of the sequence is in fact the 0 function. So this is the limit. The limit is the 0 function. What else? Right? You see how every value will, except for the 0 is exceptional value, but there is nothing is happening with 0 because it is always 0, right? It's always 0, so at 0 we have convergence to 0. Okay, and then as that flat part getting wider and wider and wider until it reaches until eventually it reaches the whole thing, it will pass every single value of x you can imagine, and which means that at that value of x the convergence will be towards 0, and therefore the limit of this sequence is 0. So this is f1, f2, f3, and this is f equal to the limit fn. Okay? So that tooth, turns out, does not make any difference in that sense, because it will be so narrow eventually that it does not affect a single value of x. But on the other hand, think about now uniform convergence. What is the distance between f1 and f? F1, it is 1, right? Okay, it will always be 1. So it's the same for f1, and the same for f2, and the same f3 for fn. The distance between these two functions, any one at the top row I take, and I measure the distance to the zero function at the bottom, the distance will be always 1 because the maximum is 1. The maximum of the difference is 1. So in the sense of the metric space that we have been talking about, there is no convergence. That the distance remains 1. Think about it. Can you approach it? Can you even speak of convergence or approximation if the distance remains 1? How do you approximate this when the distance remains 1? Okay? So even though pointwise limit exists, in fact, I probably should put it this way, like this. For each x, we have convergence of numbers, and the result creates a new function, f of x, and that is the zero function. Okay, but as far as our metric space, which we built so carefully, with big things in mind, turns out that there's no convergence. It's not the bad news; it's the good news, right? So because there is logically speaking, you do not want to assume that this is a convergence, and when you speak of polynomials, polynomial approximations, you do not want to face a convergence like that, and you don't. So I have, once again, just if you forgot a little bit about Taylor approximations, I have here an example somewhere. Oh, let me take the other one. This one. The exponential function. The exponential function is approximated by Taylor polynomials, and you can see how it starts to hug the graph of the function. So the green one is our exponential function, and then I start to build more and more Taylor polynomials. Okay, the red ones. Constant, linear, quadratic, cubic, T3. Okay, and then the last row is 4, 5, 6, and 7 degree polynomials. And there is no like a blip that would keep these two functions apart. They really start to approximate in a kind of a literal sense. They're becoming distinguishable. And that is the next challenge to worry about. If we limit our attention to an interval around 0, maybe like this, then the behavior is the match of these two functions is getting better and better, like this. In fact, look at the pictures on the at the bottom line, bottom row. You cannot even see the green line. You almost cannot see the green line. The original exponential function, you cannot see it because they are so well. It is so well approximated by the red Taylor polynomial. You can see red Taylor polynomial still varies. It changes its degree from odd to even. Right? These are odd, and those like this, those are, well, these are even. These are odd. Okay, and then but the approximation is getting better and better, and there is no separation. So the convergence is, so that's the big thing to bring back to calculus 2, is that the approximation is uniform. Taylor polynomials approximate functions uniformly, but and that's the extra challenge is it is only true when we stick to the interval, to some bounded interval, because look at what's happening elsewhere. If we just step away outside of this interval, you see what's happening. Look at this. My exponential function, it has a horizontal asymptote. In the meantime, what do we know about polynomials and their asymptotes? Polynomials and their asymptotes, what do we know about them? No. What do you know about the asymptotes of polynomial functions? It's a trick question. They don't exist, right?
We don't know.
Polynomials don't have asymptotes. Okay, so which means that there is no way this part over here of our graph over here will be, the original function will be ever approximated. So it will be, this part is almost horizontal, almost the x-axis. In the meantime, our polynomials will always run away from it. So there will be not only a gap between them, the gap will be growing as you move away from the origin, from that interval that we picked.
That would be divergence, right?
It will be, no, it won't be, it would not be uniform convergence, right? If you try to build a uniform convergence on the whole real line, then there won't be convergence because the difference will be always infinite. Okay, so we still have uniform convergence if we stick to any, no matter how large, interval on the x-axis. But beyond that, if an interval is infinite, we don't have uniform convergence. Okay, all right. So we will do a bit more of that. I will assign homework later today.